All right. So I think most of the students are here virtually. I don't know if they're physically attending the class, in the sense actually attending the class. So this is your lecture number 5. We are going to talk about divide and conquer algorithms. If at all you watch the data structures lectures, I would suggest to go over merge sort and quick sort once. And uh, I think I have covered the detailed coding and how pivot is uh, selected and how you swap in case of quick sort, and merge sort is quite simple. So you can just go over the code and actually apply the rules that we learned in this course, where you see if it's a loop in sort, what is the runtime of particular sorting algorithm based on the actual C code that we have written. Okay, so today's lecture is on divide and conquer. So you've already done divide and conquer algorithms. So we'll be discussing a few more, and we'll see how we calculate the runtime. So what is divide and conquer? You divide a problem. If you're given, let's say, let's take the sorting problem, you have to sort 10 elements. Sorting 10 is more difficult than sorting 5. Sorting 5 is more difficult than sorting two numbers. When you have two numbers, you just compare and put them in proper order. When you have 5, you have to make more comparisons and then you put them in order using any sorting algorithm. So you divide a problem into subproblems, and then you conquer means you actually solve. So first you divide, then you solve whatever the problem asks you, and then you combine the subproblems together. So sometimes in case of quick sort, we do some extra work when we are dividing. So there's no work kind of to be done when you combine. In case of merge sort, we just divide till we get to the base case, and then we when we combine, we have to do sorry, we have to do some extra work. So before going to the sorting algorithms, you must have done binary search. So you have to find an element in a sorted array. How binary search works, you find the middle of the array, middle element of the array. You check if the element you are searching for is less than or greater than this element in the middle. And in case your element you're searching for is less than, you will take the left subarray to search again. And similarly, if it's greater, you'll search the right subarray. So how do you divide in this case? You divide by finding the middle element and then comparing the element you are searching with this middle element. And based on that, you decide which subproblem to solve. Now, in this case, in case of binary search, you solve only one subproblem. You don't go, if the element is less than middle element, you'll go to the left. You will not go to the right then. So that part is discarded. Then conquer means you have to apply the same technique to the left subarray that you got now and see where your element is. And then there's no combine. In fact, you divide and conquer will itself solve your problem. So in case of binary search, this is trivial. So if you are looking for 9 in this, you will check the middle element, which is 8, and 8 is less than 9. So this is what we have to look for. Then when you have 9, 12, and 15, again, you will take the middle element, and the middle element you will compare with 9. 9 is less than, so you will take this subarray here, which has only 9, and that is your answer. Okay. So in this case, when you divide the problem, you do not have to solve both the subproblems, in the sense, both the parts of the array. So your subproblem size, if you look here, it is 1. Okay, only one subarray you have to go and check in. It's just like your binary search tree, right? If you remember, when we search for an element, we check it against the root. Then you decide whether you will go and search it in the left subtree or the right subtree. So one part of the tree is already discarded. So there's only one sub problem. There's only one subtree that you have to go and search in. And what is the size of your sub problem? It is n by 2. And what is the work you take to combine? You just have to, when you divide, you actually, in a one step, you find the middle index of the array, and then that basically helps you dividing, and that is, in combining, you don't have to do any work. So that's just O of 1. Now, if you apply, now this is our timing equation or the recurrence relation for binary search. And if you have to solve it, you can solve it using any method that you have learned. If you solve it using Master's theorem, then we find n log a to the base b, which is log 1 to the base 2, which is log 1 is 0. So n0 is 1. So if you check with Master's theorem, this will be case 2, your k is 0. And it is, I think, n to the power k and log kn or something, log k plus 1n. So your tn is theta of log n. Again, if you see, it is binary search is just like a binary search tree. You are going to search only one subtree, and the element that you're looking for may be a leaf node. So at the most, you will traverse the height of the binary tree, which is log n. So that is how you can relate this timing equation to a binary search tree. Okay. Then a similar problem comes where you have to power a number. So when you study how addition, multiplication, division is actually performed by the computer hardware, you will see that you have gates which do basic operations for you, and then based on that you build a junction of gates to do a particular operation for you, for example addition. When you have to do multiplication, it is repeated addition. So addition itself is some work, and when you multiply, you are actually doing repeated addition so many times. Let's say 5 into 100 is adding 500 times, or adding 105 times. So if you have to find power of a number, for example, x to the power 32. So x to the power 32 would mean you have to multiply x 32 times. So there'll be actually 31 multiplications. You have x and then you multiply it 31 times with itself. You get x to the power 32. Okay. Another way is that you solve this by actually finding x to the power 16 and then multiplying that value that you found by itself. So you see, x to the power 16 can itself be calculated by finding x to the power 8 and then multiplying it with itself. So again, x to the power 8 can be x to the power 4 and multiplying it with itself, so on. So you see the pattern that if you have x, you multiply, let me do it on the whiteboard. So x to the power 32, x to the power 32. If x, it's x to the power n. So I'm just dividing the problem into n by 2 and n by 2. So this will be x8, x8. So this will be x4 all the way all the way x4, then x2, x2, x squared all the way here, and which is finally x into x. So in this case, you don't, when you have x, you don't need the left branch. You can just cut it off. So x multiplied by itself will give you x squared. Once you get x squared, just a second. So just a second, just give me a second. So x square, okay, so x square into x square gives you x4. So for this, you just need x square. You don't, basically you don't have to calculate the second x square, you can reuse the value. So x4 into x4 is x8, and so on. So you, if you, okay, let me write it down. X8 into x8 is x16, x16 into x16 is x to the power 32. So if you see 1, 2, 3, 4 and 5 multiplications, instead of, would need 31 multiplications, and this way we are just having 5 multiplications. If you see, the number of multiplications is equal to the 3, 4 and the height of the tree. What is height of the tree? It is log n, right? Because it's a binary tree. So if you go back and see here, just share this. So if you go back and see here, then you just have one subproblem, just like you have in binary search, and the size of that subproblem is n by 2, and you have theta of 1. So whatever you get, you have to multiply it with itself. So that is theta of 1 at every stage. And the height of the tree is log n. If you do it by the recursion tree method, you get the runtime as theta of log n. So how do you divide the problem if n is even, like we had in our example? So x to the power n by 2, or here we have a to the power n by 2. If it's odd, then this sub problem size is n minus 1 by 2, and then you'll have to do one additional multiplication in there. Okay, so again, in divide and conquer, you will always see the subproblem size will be determined by this n by 2, n by 4, n by 8, and how many subproblems will be here. In this case, there's only one subproblem. Then you have this additional work here, which tells you whether you have to do some work while dividing, whether you have to do some work while combining. So that is your theta 1. Okay, now coming to the problem of sorting. Formally, what is sorting? You're given a sequence of elements or numbers, and you have to find that combination or that permutation of the values given in the sequence such that this is true. So they are in order ascending or descending. Okay, so how do we sort? Of all the sorting algorithms, let's discuss a simple one, insertion sort. So what do we do in insertion sort? This is the pseudocode. Let's go to the example. So insertion sort, you start with the second element, you pick it up and you compare it with all the elements on its left till you find its proper position with respect to the elements on the left. So 2, you compare it with 8, it is less than 8, so it will go on the left of 8. Then you pick up 4, you compare it with 8, you compare it with 2 and 8, and you put it between the two. Then 9 is greater than 8, so 9 will stay at its place. 3 is less than 9, less than 8, less than 4, so it will go here. Then 6 again you compare with 9, 8, and it is greater than 4, so it will go here, and you are done. So if you go back and see here, you see a for and you see a while. Okay, what is the size of the for loop? The size of the for loop, it goes from 2 to n, say roughly it is n. And what is the size of the while loop? So the size of the while loop, it is different in the sense you are not comparing all the n elements. So worst case, when you are taking the last element and you have to compare it with all the elements on the left, you can say, well, it is different at different times. So worst is it runs n times the algorithm. So before we go into the runtime, you saw there are 2 loops in the code. So runtime depends on the input, in the sense, like I said, in case of bubble sort, if the input is already sorted, then you will not, if you keep that flag option, you can get done with the loop immediately after one go only. So obviously, the smaller the size of the problem, the easier it is to sort. As the size of the input increases, the time to sort increases as well. Now, when you're sorting, using the same sorting algorithm on 2 different machines, depending on the specifications of your machine that you're using, you might be using a simple PC, you might be using a high-end laptop, or you might be using a workstation, or let's say a supercomputer to do something. So we don't calculate our runtime with respect to the specifications of our devices where we are running our programs. Because if you do that, then it's very difficult to compare. Somebody will say, oh, I finished this in like 10 nanoseconds, and you are doing it in, let's say, 100 seconds. So for that comparison, you need to know what machine is running it on, how fast the machine works, and all that. So for a general algorithm analysis, you cannot do the comparison based on the machine specs. So we say our runtime analysis is machine independent. Rather, we base our runtime analysis on the size of the input, because that's going to be uniform across any machine. If I have to sort 100 elements using machine 1, machine 2 also has to sort 100 elements. So we will compare the algorithms based on the size of the input and how size affects the runtime, not based on the specs of the machine. Obviously, there'll be differences. If we take that into consideration, it'll be difficult to compare algorithms. And again, like I told you previously, we do not consider the base case. If you see, it's written never. So you don't consider the best case, sorry, not base case. Why? Because you can say, oh, my algorithm, it can work on some input very fast. For example, bubble sort will work on a sorted sequence faster than on an unsorted sequence. So I cannot give you the best case. So I have to give you the worst case. So usually when we are talking of the runtime of algorithms, we are talking of the worst case. So that means I'm giving you an upper limit that my algo will not take more time than this time. Okay, maximum time that an algo will take on any input size. So sometimes they do average case analysis. So in that case, So you take the runtime of an algorithm over different sized inputs, and based on that you will calculate the runtime average. Okay, it's very rarely used, but mostly we'll do worst case. So again, like I said, you cannot count the machine specifications, otherwise it will become very difficult to compare algorithms. So we will compare algorithms based on how they behave for a given input size. And mostly the input size that we are talking about is the larger side of it. As in, it's easy to sort one element, it's not easy to sort 100 elements. So as n grows, how does your algorithm behave? So maybe sometimes the performance of some algo will go up as n increases, but as n tends to infinity, it will dip down again because of whatever way it is scheduled. So we have to consider that as well. So that's why we'll go with input size for comparison of algorithms. So look at the growth of your Tn as n tends to infinity. Now, coming back to our divide and conquer methods of sorting. So you have merge sort, quick sort, both are divide and conquer, and both you have done previously. So I'll not go into the uh, details. So let's just see this, then we'll come back to this slide. So what are the steps? This is a pseudocode for array of size 1 to n. If n is 1, it is already sorted. If otherwise, you find the middle point and you divide your input into two arrays, one from 1 to 1 n by 2 and another from n by 2 plus 1 to n. And once you are done dividing, then you merge the two sorted lists. So key subroutine is merge because your actual work of sorting is done in merge. So what does merge do? Okay, before going there, your merge sort had to sort n elements. This is theta1 is the time to sort one element. Now you're breaking your problem into two subproblems of size n by 2, and then you are comparing and then putting the elements in order. Okay. Now, if you go back to my data structures notes, you'll see why the merging is theta of n. So let's go to the example first and then I'll come to this in a while. Okay, so this is your example. Dividing is simple. You divide and you're actually just splitting them apart, splitting the array apart into two halves and then two halves, then like this for all of them. Okay. Then when you have to merge, you go, yeah, let's do that here. So you have 4 and 10. You compare the first element of the left side, which is 4, with the first element of the right side, which is 10. 4 is less than 10. So when you will merge it, you'll put them like this, 4 and 10. Similarly, 3 and 6. 3 is less than 6. So you get 3 and 6 in the same order. 2 and 8. Okay, they've written it wrongly here. It is 8 and 2. So it will be 2 and 8. 5 and 7 is 5 and 7. Let's forget about the lower order here. Okay. If you look at this level, first you'll compare 10 with 8. Okay, so 8 is smaller, so 8 goes first in your resultant array. Then Since 8 is gone, this pointer will move ahead. You will compare 10 with 2. So 2 is smaller, 2 will go in the resultant array. Then you'll compare 10 with 5. 5 is smaller, 5 will go here. 10 with 7, then 7 will go here. Okay. Now this array is exhausted. So actually when you're merging, we got, no, we did it wrong, sorry. We have to do it on the next slide. Actually, this is already sorted. Let me do it on the whiteboard. It's better. So let's say 2, 8, 10, 21, 5, 15, 22. When this is the second last array on the way back of merging. So I'll have 2 pointers, one pointing here and one pointing here. So I'll compare the first 2 elements, 2 and 1. Whichever is smaller goes in the resultant array. And since 1 moves, this pointer moves here. Then I compare 2 with 5. 2 is smaller, so 2 goes in the resultant. This pointer moves ahead and this pointer stays, the 5 one. 8 and 5, 5 comes here. Okay. Then 8 and 15, 8 comes here. 10 and 15, 10. Then 20 and 15, 15, 20 and 20. This is how it will be sorted. So if you see, what is the maximum numbers of comparison you'll have? When you compare, then only you put an element here, right? So it doesn't matter which element from which subarray comes first. When you compare, then you put an element in the final list. So how many times will you compare? Equal to the number of elements in the final list. Okay. So you might not compare n times, you might compare less than that. So I'll show you how many comparisons we did. Okay. 2 with 1, with 5, 8 with 5, 3, 8 with 15, 4, 10 with 15, 5, 20 with 15, 6, 20 with 22, 7. So 7 comparisons and 22 came in place itself. So at the most, n comparisons. It is possible that you have something like this. 2, 8, 10, 20. And all the values on the right hand side, suppose, are greater. So when you compare 2 with 22, 2 will go first. 8 with 22, 10 with 22, 20. So n by 2 comparisons. So this is the best case, that you'll have n by 2, and worst case you'll have n comparisons. Okay. So for every level, depending on what is the total number of elements you're going to get after merging, those many comparisons is the maximum that you will make. So just go back here. So for merge sort, you will divide the problem into 2 subproblems of size n by 2, and you will have to do some extra work for dividing and combining. Dividing an array into 2 is not a big task. You just find the middle index and then you just pass on the next array as between 0 to that middle point and middle point plus 1 to n. Okay, so this is the runtime. If you have one element, that's the base case, Tn is theta 1, otherwise it's 2 Tn by 2 plus theta n. So theta n is what we generally replace with C into n when we have to solve this equation. So this is the equation. If we do it by recursion tree, Cn is Tn by 2 n by 2. We did this example before as well. So at every level, the height is log n. At every level, the amount of work you are doing to merge two arrays of size n by 2 and n by 2, you have n comparisons. To merge two arrays of size n by 4 and n by 4, you have n by 2 comparisons and n by 2 comparisons. So overall, again, it will be C of n. Okay, so on. So every level you do at the most n comparisons. Height of the tree is log n. So the total runtime is n log n. This is for your merge sort. So merge sort is very clear. There's no discrepancy in the sense we always get half partitions. Uh, for even, obviously, we'll get very good partitions, balanced, exact balanced tree. For odd, we'll just get somewhere it'll be a little off. It won't be a perfectly balanced tree, but then it won't affect the runtime as much. So, okay, so n log n grows slowly than n square. If you remember that graph, you have n log n, and then n square. So merge sort, it beats insertion sort in the worst case. So in practice, they have seen that when n is greater than 30, it is always the case. So basically that is your n0 in this case. Now coming to quicksort. Quicksort algo, same way we divide the problem into subproblems, again a divide and conquer. How the only thing that differs between quicksort and merge sort is that when we divide, that's when we decide which elements goes where. In merge sort, we just divide. जो left sub array में है, जो first 4 position, let's say if size is 8, they will go to left all the time and rest will go to the right. In quick sort, who will go to the left sub array and who will go to the right sub array will be decided by the pivot element. So the main important task is to find a pivot element which will give you almost a equal partition. Because if you don't get an equal partition, your runtime will not be n log n. We will see that in a while. So if this is the array, if you remember last time, I think we picked up the last element of the array as the pivot. Here in this example, they're picking up the first element of the array as the pivot. You can select the pivot in any other way, but since the selection of pivot is very important in deciding how the array will be split, normally they try to find a more suitable pivot which will give them a more even division of the array. So let's say 40 is a pivot element. What happens in quicksort? You pick a pivot and then you check it against, you keep 2 pointers here. Okay, you have 2 pointers, one pointing to 20 and one pointing to 100. These 2 pointers, the left pointer will move ahead till it encounters elements which are less than 40. Once it encounters something which is greater than 40, it will stop. And the same is the case with the right pointer. It will keep moving left till it encounters elements which are greater than 40. Once it encounters something which is less than 40, it will stop. So first we are on 20, 100. 20 is less than 40. So it will move ahead. 100 is greater than 40. It will move backwards. So first one has moved to, even 10 is less than 40. So it moves to, reaches 80 here. And this is at 100. This will go to 30. Now 80 is greater than 40 and 30 is less than 40. So these pointers cannot move ahead when they encounter such a situation. So what happens when both are stuck? They swap the two values. So 80 comes in place of 30 and 30 comes in place of 80. So 30 is less than 40. So now this pointer can move ahead, the left pointer. This is your left and this is your right. So then again it gets stuck on 60 since it is greater than 40, and this one gets stuck on 7 as it is less than 40. So again we'll swap the two. Then again left pointer will move ahead to 50 and right pointer will also move ahead. So if you remember, when these pointers they cross over, then we stop this partition process. So 50 is greater than 40, so left pointer will cross over. Now the crossover happened. The left and the right pointers have crossed over, and that is when we stop and we replace the pivot element with the crossover point. It's pointing to 7. We replace it with that because 7 is less than 40, so it can safely take its place. I think in the data structures notes, I had put the last element as the pivot. So you will switch the last element with that element which is greater than 40, which will be the right, this one, if you were using that pointer. So you can just check those notes and see. So now 40, what happens at the end of quicksort? At the end of first partition of quicksort, the pivot element comes at its final location. So 40 will be there because all the elements less than 40 are on the left, all the elements greater than 40 are on the right. Now you have 40 is in place. What you are worried about is this and this. So this is what you would apply your recursive quicksort, as in these are your subproblems now. To find the subproblems, you had to put this much effort of comparing elements. So again, how many elements have you compared? You compared all the elements with the pivot. So there are, let's say, excluding the pivot, there are n minus 1 elements. So at the most you made n minus 1 comparisons to move the left and the right pointers, and then you got 40 in place. So your divide is taking time. Okay, you won't have to do anything in merging in this case because at the end of divide, one element comes at its proper position. Okay, so we ideally say when quicksort pivot is selected properly, you will get an even division. So if we get an even division, then we get the equation. Then we get the equation that Tn is twice Tn by 2 plus C into N. If your pivot is able to divide the array into n equal halves at every level, because this equation is true when you get a binary tree type of structure for division. So even if you select the best of the pivots, it is not possible to get the exact half division at every level. But you'll see that even if the divisions are not equal, even if they have some kind of a ratio between them, you get something which is of the factor of log n. That is a bit of complicated maths for you now. So the average case, like I said, the average case sometimes we do, and we do that for quicksort. It is something of the order of log n. So same recursive equation, you'll get the same answer, n log n. Now, if you get a very bad selection of pivot, for example, in this case, if you choose 2 as the pivot, so 2, if you see, is the smallest element. So when you divide based on pivot 2, all the elements greater than 2 are going to be on the right hand side. There is no element less than 2, so on the left hand side you have nothing. Okay, so 2 is at its place. So what division did you get this time? You got 0 in the left subarray, then you have 2 in place, and you have 8 in the right subarray. So again, if you see, this is a sorted array. So that's why when you'll always get 0 elements on the left and rest of the elements on the right. So again 4 is selected. Okay, this is your first partition. So what is the partition size? If you had Tn, Tn is equal to how many elements left in the subproblem? Tn minus 1 plus T0 in the left and plus C into n. That is for division by selecting the pivot. So if we come here on the whiteboard, just iterating n minus 1 plus n. Tn minus 2 will be Tn minus 3 plus n minus 2 plus n minus 1 plus n. Generalizing n minus k, this is n plus n minus 1, just reversing, plus n minus 2, so on, plus n minus k minus 1. So when n is equal to k, then you get t of 0 plus n, n plus n minus 1 plus n minus 2 all the way, n is equal to k, so you get 1. So this is sum of the elements from 1 to n, which is equal to this. So this is your n square. So if you get this kind of a partition at every stage in a quicksort, your pivot element is very badly selected, then you will get this timing equation and you will get n square. So the worst case for quicksort is n square. So best case is n log n, worst case is n, and balanced case, let's not go into that maths because it will be very difficult to do it on the board. Average case analysis is also of the order of some log n, not to the base 2 because the partitions are not like half and half in that case. So here you see they mentioned depth of the recursion tree is O of n. So obviously you're going from Tn to Tn minus 1 to Tn minus 2. So if you make it in the form of a recursion tree, you will see it'll go all the way to T1, which means that the tree, if you create, will have depth n. And how many at every level you do n work for partitioning. So n into n, n square. So that way also you can do that. You can do the runtime analysis. So now, how do we avoid the worst case? Because n square is not a good time to sort. We avoid by uh, carefully choosing the pivot. Sometimes they know what kind of input you're going to get. Okay, because we're not talking about, let's say, n equal to 5, n equal to 10. There it doesn't even matter when you have to sort. When you're talking of huge numbers and huge data that you're sorting, then worry about the time and speed. So if you have an idea of what kind of input you are getting, you might uh, kind of predict the average values will be in this range. So you can select a pivot accordingly. Okay, choosing a good pivot element is essential. Okay, you can have an improved pivot selection, you can have median, you can have average, you can have some probabilistic if you think the probability of getting numbers are in this range, then you can apply mathematical functions to determine some kind of a pivot, which gives you a good even partitioning in case of quicksort. And then your sorting will be faster, in the sense the runtime will be less than n square. Okay, so that is for your quicksort. So sorry. In conclusion, if you look at divide and conquer, you'll see there are other algorithms which we are going to do next, like dynamic programming. They also use recursion. They also use, in a way, it is divide and conquer, but it's not exactly divide and conquer. We'll see the differences. You do divide your problem into sub-problems. And obviously, when you write a problem uh, in terms of itself, it will be recursion. But it depending on how we are doing the calculations, it is not always divide and conquer. It is given different names. the next the next algorithm that we will study is dynamic programming, which is similar to divide and conquer, but it is not divide and conquer. So we'll see why and how. Okay, so I think that is it in case of this, but go through, if you have some confusion in Quicksort, at least understand Quicksort, you can go over the previous notes, the handwritten notes. I think I have also demonstrated an example there. So you can go over Quicksort, merge sort, insertion sort for this. And we have done binary search. You can just, if you're not clear what binary search is, study that again. And powering a number. So also, I forgot to mention it. I'll just add it to the notes here. You have also done binary search trees and data structures. So when you are searching in a binary search tree, if you are looking for a maximum or a minimum, again, it is a kind of divide and conquer. When you're searching for an element in a binary search tree, again, it is a form of divide and conquer, because you are, if you, just a second, if you, so if we see a binary tree, it may or may not be balanced. It can be something like this, say 100. Just putting some random, 200, 450, can be 91. Okay, so when you have to search for something, let's say I'm searching for 450. Okay, you come here, you check if 450 is greater than 100. So you know it is in this right subtree. So this part is already cancelled out. So let's say we don't know whether a binary search tree is balanced or not. That balancing is done in other type of trees, height balancing trees, AVL trees, etc. If we get time towards the end, we'll just go over those. We might also do B trees. So basically they do a height balancing, in the sense you will not have empty levels here. Uh, no, you might have empty levels, but the height difference between left and right will be at most 1. So that way they balance, keep the tree always balanced. You won't see something like this. You won't see something like this. This will not be allowed in that case. Okay, so when you go searching in a binary search tree, if you have n elements searching, again, you are dividing your problem into half. That's what we assume if it's a balanced tree. And there'll be almost n by 2 elements on the left and almost n by 2 elements on the right. So you only have to check what you only have to check you first compare with 100, that is this comparison, and then you go and look for 450 in the rest of the tree, which is n by 2 size. Then again, next, when you do Tn by 2 is Tn by 4 plus 1 plus 1. So when you compare it with 50, then you will just consider this part of the tree. And the next step, Tn by 8 plus 1 plus 1 plus 1, so on. Then you will reach here and you find out. So how many ones will be there? There are 3 ones. So if this is n by 2 to the power 3, this is 3 times 1. So if n is equal to 2k, do it here. If n is equal to 2k, k is log of n. So this is your k here. So this will be t1 plus log of n. So again, in case of merge sort, we didn't have 1 at every level. We had n at every level. In this case, we have a comparison with the root. So that is one unit of work to be done. So 1 into height of the tree is log n. Okay. In case of merge sort, you do n work and you're actually following both the branches. So it is n into log n. So your binary search tree, most of the algorithms, even when you do add or if you do delete, you remember for adding also you have to go to the proper location. So you don't have to go and search the entire tree to see where you have to put. You have to follow a specific path. And if you remember, what is the path that you follow? So similarly, if you have to, let me just erase this. If you have to make a tree and add something, for example, you have to add some a, and by way of its value, it will be put here. So how many steps do you need to follow? 1, 2, this is where you'll put it. So again, the height of the tree, which is of the order of log n. If you have to delete something, let's say you have to delete this node. Okay, so to get to this node, you have to again follow the height of the tree, which is log n, and then deletion has some cases you have to see whether that is followed, but overall it is log n. If you remember your heaps, heap is a complete binary tree, so any percolate up or down will just travel across from root to the leaf or leaf to the root. So it will maximum time it will use is equal to the height of the tree, which is log n. So that's why heap is supposed to be faster in terms of its runtime. When you're going to look for a maximum or a minimum, already some work has been spent in constructing, and even if you have to edit the heap, you have to, the adjustments to be made in the tree will take you time of the order of log of n, which is not bad. So you can go, that's why heap is also known as a priority queue. Priority queue is something where elements are given priority, so that priority in the sense that when you come to pick up some element, you want the highest priority element, you will get that in, you just go and get that element, and the rest of the readjustment of the heap has to be done in the background. So the time to search is essentially that one step you go and you pick up the root from the heap, and then the heap readjusts. That is kind of, once I get the element, I'm not worried about how they adjust the back at the back end. So that doesn't affect my retrieval time. That is a background adjustment they have to do. Even if they have to do it, even if I am affected, let's say I want to do constant accesses to the elements in the heap, log n is the time it will take the heap to adjust and get me the next maximum or minimum on top. So that is the best time you can get for any job done when it's of the order of log. Okay, I'll just edit this slide a little more, add let's say 1-2 slides on binary search trees and heaps, and then I'll upload it on in the classroom. Okay, So this is the end of it. This is pretty much what you have done already. Just go over it. If you have any questions, you can also email me. Okay, Aman, please take the attendance.
Yes,
If
ma'am,
you
I have
haven't
taken it.
already. Have you taken it already?
Yes, ma'am. Yes, ma'am.
I can't hear. You can just write in the chat box. Okay, all right. All right, thank you. We'll I'll see you in the
Thank
next
you, ma'am.
class. See your nameless in the next class. Okay, thank you everybody. Bye.
Thank you, ma'am.
Thank you, ma'am.